Hi everyone, today we'll be looking at paper 1, Pure Mathematics 1 of June 19. Question 1, we're given f of x here in terms of a, and we're also told that the x plus 3 is a factor of f of x, and we need to find the a. So x plus 3 being a factor certainly means that f of minus 3 must be 0. So if we just substitute here x with minus 3, we will be getting an equation in terms of a, and this is giving me minus 81 plus 18a plus 12 plus 5a being 0, so 23a is 69, and therefore a is 3. So for 3 marks to obtain the value of a. Question 2, we have this plot. It's not a sketch, it's a plot, and we are being given cos x, and we need to use diagram 1 to show why this equation has only one real root. So I could start off by considering the scaling on the axis. We know that cos x varies between 1 and minus 1. So we've got 1 here and minus 1 here. We also know that it has a period of 2 pi, so this is 6.28, which means that each of these squares is a unit. So I'm just going to quickly scale the axis here. So this is cos x. In order to determine solutions to the given equation, I could simply rearrange into cos x is 2x plus a half. So drawing the line y is 2x plus a half will allow me to identify points of intersection. So we could, for example, consider x is 1. When x is 1, y turns out to be 5/2. So we know that the line passes through 1 and 5/2. It's also passing through 0.5. That's the y-intercept. So if I just draw the line here, y equals to 2x plus a half, we can see that we have one point of intersection and therefore one real root. So that will give me the second mark. So only one point of intersection. Hence, only one real root. In B, we need to use the small angle approximation for cos x to estimate the value of alpha to 3 decimal places. Now, certainly, we are in radian mode here for the small angle approximations to hold true. We are told in the formula booklet that cos theta is approximately 1 minus theta squared over 2. So what I will do is actually use that. So cos alpha minus 2 alpha minus a half is 0. So 1 minus alpha squared over 2 minus 2 alpha minus a half is 0. This will be leading to a quadratic in alpha. So if I multiply throughout by 2, I get 2 minus alpha squared minus 4 alpha minus 1 is 0. So 0 is alpha squared plus 4 alpha minus 1, which is can be solved using the quadratic formula, and it's giving me answers of minus 2 plus minus root 5. Now, I cannot accept both of these because we are told that it's the value of alpha that we need to estimate. We pick the smallest of the two, the one that's closest to 0. So we're gonna pick minus 2 plus root 5. And because we are told to give answers to 3 decimal places, that's gonna be 0.236. So that was the second question. In In the third question, we need to differentiate here. We could be using the quotient rule here. So dy dx, we differentiate the top 10x plus 10, and we keep the bottom, minus keep the top, differentiate the bottom, so we get the power down, we deduct 1 from the power times the derivative of the bracket, and all over x plus 1 to the power of 4, because it's the bottom squared. Now, I can factor out the 10 here, and I'm left with x plus 1 squared, minus 5x, x plus 2, times 2x plus 1, and all over x plus 1 to the power of 4. I can actually factor out the x plus 1 and the 10, so 10 brackets x plus 1, and I'm left with x plus 1 squared minus x plus 2, and all over x plus 1 to the power of 4. Now the x plus 1 with the x plus 1 to the power of 4 is simplifying, and I will also expand to get x squared plus 2x plus 1 minus x squared minus 2x over x plus 1 cubed. And we've got further simplifications, the x squared with the x squared and the 2x with the 2x, leading to 10 over x plus 1 cubed. And this means that we can just state that a is 10 and n is 3. Hence, deduce the range of values of x for which dy dx is 0, is less than 0, sorry. So we want 10 over x plus 1 cubed to be less than 0. Now, 10 is obviously positive. The only way for all of the left-hand side to be negative is for x plus 1 all cubed to be negative. And this will be negative if x plus 1 is negative, so x is less than minus 1. In 4, we need to find the first 3 terms in ascending powers of x of this binomial expansion. So we start off with 4 minus x to the minus a half. We need to force the 4 out. It inherits the power. I'm left with 1 minus x over 4 to the minus a half here. 4 to the half is 1 over 2, and then I apply the binomial expansion, which is given in the formula booklet. I need to go up to the term in x squared, so it's 1 plus minus a half minus x over 4 plus minus a half minus 3 over 2 over 2 factorial minus x over 4 squared plus dot dot dot. This is a half, and I have 1 plus x over 8 plus 3x squared over 128 plus dot dot dot. We need to give final answer in simplified terms, so this is simply a half plus x over 16 plus 3x squared over 256. So that was the first part of this question. Then we are being given 3 possible values for x, and we need to state which one cannot be used for approximating root 2 and which one will give the most accurate approximation to root 2. Now we know that this expansion is actually infinite, meaning that it goes on forever. So we know that the expansion is valid for modulus of x over 4 being less than 1, which means that x has to be between minus 4 and 4. And therefore, using x is minus 14 is outside the validity range. So x is minus 14 is outside the validity range. So it cannot be used. And for I, which one of the two values, the remaining two values, will lead to the most accurate approximation to root 2? Then we pick the one that's closest to 0. So use x is minus a half as it is the closest to 0. The smaller the value of x that we use, the more rapid the convergence to the desired value is, and therefore the more accurate the approximation. So using x is minus a half is the right answer in this last part of this question. In 5, we need to put the f of x in the required form. So we need to complete the square here. So 2x squared plus 4x plus 9. I can factor out the 2 here. I'm left with x squared plus 2x and the plus 9. And then I complete the square. It's x plus 1 all squared minus 1 and the plus 9, which is 2 brackets x plus 1 squared minus 2 plus 9, leading to 2x plus 1 squared plus 7. Now, if you are not in the mood of completing the square, an alternative approach would be equating coefficients. So you've got 2x squared plus 4x plus 9, and you set that equal to ax plus b squared plus c, which is ax squared plus 2abx plus ab squared plus c. So if we just compare now the coefficient of x squared, we get that 2 is equal to a. So a is 2. We could also compare the coefficient of x, so 4x with 2abx. So 4 is 2ab, and knowing that a is 2 leads to 4 is 4b, so b is 1. And finally, what we can look at is the constant term, which is 9 on the left and ab squared plus c on the right. So we simply say that 9 is ab squared plus c. We have the values of a and b, and this will give me c to be 7. So still scoring full marks here. And then we need to sketch the curve f of x, showing any points of intersection with the coordinate axis and the coordinates of the turning point. So because we actually went into the trouble of putting it in this particular form, f of x is 2x plus 1 squared plus 7, we certainly know that the shape is a smiley one. We know that when x is 0, y will turn out to be 9. And we also have the turning point, which is actually a minimum. We know this from the shape, which is when this is 0, so when x is minus 1, and when x is minus 1, y is 7. So at x is minus 1, we will actually find also the line of symmetry of this parabola. So what we have here is something like this. This is 9, the cut on the y-axis, the minimum is at minus 1, 7. So this will be qualifying for full marks in this part B. And then for C, we need to describe fully the transformation that will map f of x onto g of x, which is given here. So somehow we need to find a way of associating f of x with g of x. I think what I can do is first of all start by writing that f of x is, we said 2x squared plus 4x plus 9, and then we've got g of x, which is, we said 2 brackets x minus 2 squared plus 4x minus 3. So it would be actually great if we managed to get the x minus 2 here as well. So I'm just gonna say this is 2 brackets x minus 2 squared plus 4 brackets x minus 2, which is introducing an extra minus 8. So if I put a plus 5 here, I will be getting an overall minus 3. So if we compare now with f of x, we see that x has now been replaced by x minus 2, which is essentially a translation 2 units to the right, and then 9 became 5, so we've got a decrease by 4 in the y, so this is a translation by the vector. So 2 to the right and then 4 down, 2, negative 4. That's the CI. In CII, we need to be considering h of x, which is 21 over 2x squared plus 4x plus 9. So, and we need to give the range of the function here. So what I plan on doing is actually start from what we were given, the 2x squared plus 4x plus 9, which we have written as 2 brackets x plus 1 squared plus 7. So we know that this is attaining values between 7 inclusive and infinity. We can see this from the graph. So if we go back to the graph, we see that the range of values is from 7 onwards. So from 7 up to infinity for all x in the real numbers. So if I take the reciprocal of this, 1 over that, then what we will be seeing is that the original minimum becomes now a maximum, so it's less than or equal to 1 over 7, and on the left hand side it's 1 over infinity, which is essentially a 0. So we've got the inequalities reversed essentially. So when originally I was greater than or equal to 7, I'm now less than or equal to 1 over 7. And then if I multiply throughout by 21, I get that on the left hand side I'm still looking at a 0, and on the right hand side I've got 21 over 7, which is simply 3. So what we have done here is essentially reconstructed h of x, having as our start point the original 2x squared plus 4x plus 9. So we see that the range of values of h of x is from 0 to 3, 3 being inclusive and 0 being excluded. In question 6, it's a trigonometry question. We need to solve this equation, which is given in degrees. So we've got that 5 sine 2 theta is 9 tan theta. We can start off by writing sine 2 theta as 2 sine theta cos theta, and 9 tan theta as 9 sine theta over cos theta. We can then actually cross multiply to get 10 sine theta cos square theta being equal to 9 sine theta. Do not divide by sine theta at this moment, but just collect everything on one side and factor out the sine theta to give you 10 cos square theta minus 9. So either sine theta is 0 or cos squared theta is 9 over 10. This is a quadratic in cos, so we actually need to split it into cos theta being the root of 9 over 10 or negative root of 9 over 10. We need to generate the principal values here. So for sine theta being 0, the PV is 0. For cos theta being the root of 9 over 10, we get a PV of 18.4. And for the last equation of cos theta being minus root of 9 over 10, we get the PV to be plus 161.6. So we know that for sine theta being 0, theta is 360n plus 0, or 360n plus 180 minus 0. We've got theta is 360n plus minus 18.4, and theta is 360n plus minus 161.6. So we are varying between minus 180 and 180 inclusive of both boundaries. So the solution should be minus 180 minus 161.6 minus 18.4, 0, 18.4, 161.6, and 180. We need to be particularly careful here because the boundaries happen to be inclusive and also solutions of the given equation. Now in part B, we need to deduce the smallest positive solution to the equation. It doesn't take long to realize that theta has been replaced by x minus 25. So if theta is x minus 25, then we need to pick out the smallest positive solution. So we've got the solutions for theta. So theta plus 25 is x. So actually picking out minus 18.4 will give you the smallest positive answer. So minus 18.4 plus 25 is x. So x is giving me 6.6 degrees. Seven, we've got a simple model here. It says of the value v of a car depending on its age t measured in years. We are given that originally the car is worth 20,000 pounds and the year after it drops to 16,000. So we really need to use an exponential model to form an equation for the car as a value linking v with t. The fact that we've got an exponential model means that we're looking at the model of the form v is v naught e to the kt. Now we know that when t is 0, v is 20,000. So if we just substitute this here, we get that v naught is 20,000. It's actually the initial value. That's why we call it v naught. And we also know that when t is 1, v is 16,000. So if I substitute here 16,000 for v naught has already been found to be 20,000 e to the k because t is 1. Then I can simplify the 3 zeros on either side, and I get 16 over 20 is e to the k. So ln of 16 over 20 is k. So we can just say that v is 20,000 e to the ln of 16 over 20 times t. That will be the model for car A. B, we are monitoring, it says, the value for the first 10 years, and we found that after 10 years it is worth 2,000. And we need to evaluate the reliability of the model. So if the model is indeed a good one, then when t is 10, we expect an answer that's close to 2,000, which was the actual value observed after 10 years. So V is 20,000 e to the ln of 16 over 20 times 10. My calculator is giving me a value of 2,150 pounds. This is close to the observed value of 2,000. And hence, we can say that the model is reliable. In part C, we've got a different car now, car B. It starts off with the same original value and then depreciates more slowly, drops value more slowly. So how could we adapt the equation? Well, we still have the same value, so our V naught will still be the same, but in order to control and reduce the rate at which the car depreciates, we need to use a value that's less negative than ln of 16 over 20. So what we have to do here is simply say that we need to make ln of 16 over 20, which is minus 0.223, less negative. If you think about it, if this was 0, it means that the price is not changing, the value is not changing. The more negative it is, the faster it drops, the faster it depreciates. So if we make it less negative, bring it closer to 0, but still negative, it is decreasing, but not as quickly as car A. So that's what the examiner was expecting us to do in part C here. In question 8, we've got a sketch of the curve shown here. Equation x plus 2x minus 4. We need to show that the exact area of R1 is 20 over 3. So by inspection, we know that the cuts on the x-axis are at minus 2 and 4. So R1 is given by integrating from negative 2 to 0, a given equation, which is upon expansion x cubed minus 2x squared minus 8x. So this is a simple integration. We increase the power by 1, dividing by the new power. And then we substitute the limits in. So upon substitution of 0, everything becomes 0. And then we've got the negative 2 substituted in x. And this is giving a result of 20 over 3 as required. So that was part A. We are then told that the second region, shaded as R2, is bounded by the positive x-axis, the curve, and the line with equation x is b. B is between 0 and 4. And given that the two areas are equal, we need to verify that B satisfies the given equation. So, because R2 lies entirely below the x-axis, when we integrate, it will give numerically a negative value. And because the area is 20 over 3, we know that the integral from 0 to b will be minus 20 over 3. That will be my starting point. So from 0 to b, integrating x cubed minus 2x squared minus 8x dx should be giving me a value of minus 20 over 3. So we have the integral here. We said it's x to the power of 4 over 4 minus 2x cubed over 3 minus 4x squared from 0 to b. So if we plug in b, we get that b to the power of 4 over 4 minus 2b cubed over 3 minus 4b squared. When I plug in 0, I get 0, is equal to minus 20 over 3. The idea is to collect everything on the left, the right hand side being 0, and then also getting rid of any fractions to see what we get. So the LCM here is 12. So we have 3b to the power of 4 minus 8b cubed minus 48b squared plus 80 equal to 0. Now this is a quartic in B. The question was asking us to actually show that, verify actually that that's the equation being satisfied. So I think I will be stealing this printed answer, expanding, and hopefully showing that it gives me the same exact expression that I arrived through integration. So b plus 2 squared brackets 3b squared minus 20b plus 20. I don't know whether it's 0, I will expand it. So it's gonna be b squared plus 4b plus 4, and then brackets 3b squared minus 20b plus 20, and then a further expansion to give me 3b to the power of 4 minus 20b cubed plus 20b squared plus 12b cubed minus 80b squared plus 80b plus 12b squared minus 80b plus 80. I will actually look for simplifications here. So we've got the 80b with the minus 80b. We've got to simplify all of that now, and this is giving me 3b to the power of 4. Looking at the b cubed terms, it's minus 20 plus 12, which is minus 8 b cubed. The b squared terms, 20 minus 80 plus 12, it's minus 48 b squared plus 80, and this is 0. Hence b satisfies given equation. The fact that the prompt here was for us to verify is actually an indication that we can actually use the printed answer to show the given result. And then our part B in C, we are told that the two roots of the quadratic here are 1.225 and 5.442. The value of b is therefore 1.225 because we have the restriction of b lying between 0 and 4. And we need to explain with the aid of a diagram the significance of 5.442. So I will start by drawing a diagram here, and then we will see exactly what's happening here. So we will quickly draw the curve again. Now this was minus 2, this was 4. We know that all of this is 20 over 3. And we have also found that if b is here, which we are told is equal to 1.225, then this is also 20 over 3. And then there's another solution, the 5.442, maybe somewhere here. And we need to explain the significance of that value, the 5.442. So now, integrating from minus 2 to b will give me a result of 0 because the two areas match. One is above the x-axis, so it's contributing positively. The other is below the x-axis, so it's contributing negatively. So overall, they cancel out. but they would also cancel out if I integrated from -2 to 5.442. So this means that from -2 to 5.442, the total numerically area is 0, which essentially means that the area above with the area below will cancel out so that they are matching. So what we need to say is that between x is -2 and x is 5.442, the area above the x-axis is equal to the area below the x-axis. So this part and this part added up are equal to the part below. Question 9 is a question on logarithms. We are told that we've got a being greater than b, greater than 0, satisfying this. And we need to show that a is b squared over b minus 1. I will start by combining the log a minus log b expression into a single logarithm. So it's going to be log of a over b. I'm just using the rules of logarithms here. And since we've got one logarithm on either side, we can equate a over b with a minus b. Cross multiply ab minus b squared. We need to make a the subject here. So b squared is ab minus 1, leading to b squared over b minus 1 being a as required. In b, we need to write down the full restriction on the value of b, explaining the reason for this restriction. So what we need here is a being positive. That's what we have. A is positive. So we just write, since a is positive, b squared over b minus 1 must be positive. And then b squared is always positive, so since b squared is always positive, b minus 1 must be positive, so we want b to be greater than 1. So this is what we have here. We want b to be greater than 1 in order for b to attain a valid value. In 10, we need to prove that for all n in the naturals, n squared plus 2 is not divisible by 4. So we will just split the set of natural numbers, the set of positive integers that is, into odd and even numbers. So consider n is 2k and n is 2k plus 1 for k in the naturals. This means I've just reconstructed the set of positive integers. Actually, to be correct, I also need to include the value of 0 for k. So I'm just gonna say k is 0, 1, 2, 3, and so on. Now, n squared plus 2 will be 2k squared plus 2, which is 4k squared plus 2. Certainly not divisible by 4 because it's a multiple of 4 plus 2. So it's a multiple of 4 plus 2, hence not a multiple of 4. And And then there's the other chance that n squared plus 2, we start with the odd number, 2k plus 1 squared plus 2, which is 4k squared plus 4k plus 1 plus 2, which is 4k squared plus k plus 3, a multiple of 4 plus 3. Again, not divisible by 4, hence not divisible by 4. We certainly need an overall conclusion here, hence for all n in the naturals, n squared plus 2 is not divisible by 4. So always write down the conclusion in order to secure full marks. And in II, given that x belongs to the reals, the value of 3x minus 28 is greater than or equal to the value of x minus 9. That's the proposition. So the absolute value of 3x minus 28 is greater than or equal to x minus 9. We need to state, giving a reason on whether this statement is always true, sometimes true, or never true. Now, if we feel that it's sometimes true, we need to provide numerically an example when it's true and when it's false. If it's always true or never true, we need a solid proof of this being the case. In this particular case, it's actually sometimes true. You need to come up with particular values for x. So if I put x to be, for example, 9.4, I get 3 times 9.4 minus 28, which is equal to 0.2. And 9.4 minus 9 is 0.4, so false, because 0.2 is not greater than or equal to 0.4. And on the other hand, if I put, for example, x is 0, I get the modulus of 3 times 0 minus 28 being 28, and 0 minus 9 being negative 9, so in this case it's true, hence sometimes true. You could have approached this through a series of sketches or simply providing numerical examples. In 11, we've got a competitor who is running a 20-kilometer race. She's running the first 4 kilometers at a steady pace of 6 minutes per kilometer, and after the first 4 kilometers, she's slowing down. She's slowing down so that each subsequent kilometer will take her 5% more time than the previous. So we need to show that the time to run the first 6 kilometers is 36 minutes, 55 seconds. So I could actually come up with a table here. First of all, we know that first 4 kilometers are at 6 minutes per kilometer. And we've got a sequence evolving from the 5th kilometer onwards. So the 5th kilometer will be done in 5% more, 6 times 1.05. The 6th kilometer will be 6 times 1.05 squared. The 7th kilometer, 6 times 1.05 cubed. We have a geometric sequence evolving here. So I will just say that the total time for first 6 kilometers will simply be the time for the first 4, which is 4 times 6, plus 6 times 1.05, plus 6 times 1.05 squared. This is giving me a result of 36.915, which is 36 minutes and 55 seconds as required. Now in B, we need to show that the estimated time to run the Earth kilometer is given by this expression. I can actually look back to my table. I have invested some time setting this up so I can easily generalize into the Earth kilometer being 6 times 1.05 to the r minus 4 by merely observing that the difference between the kilometer and the index is just the kilometer minus 4. So I'm just gonna say that from the above table, the time to run the Earth kilometer is 6 times 1.05 to the r minus 4 as required. So the justification for me getting the mark will be the table and the explanation here. And then C, we need to estimate the total time in minutes and seconds that she will take to complete the race. So the total time will obviously be the 6 times 4 for the first 4 kilometers, and then it's gonna be 6 times 1.05 plus 6 times 1.05 squared up to 6 times 1.05. The 20th kilometer will be to the power of 16. So we've got a total here of 16 terms. So n is 16. The first term is 6 times 1.05 and the common ratio is 1.05. I will be using the formula for the sum of the first n terms of a geometric sequence. So it's a 1 minus r to the n over 1 minus r. This is giving a result of 173 minutes and 3 seconds. Now, the next question is 12. We start off with f of x being 10 e to the minus 0.25x sine x. We need to show that the x coordinates satisfy the equation that tan x is 4. So what I actually need to do is do differentiation here. I will be applying the product rule. So f dash of x will be differentiate the first, so minus 0.25 e to the minus 0.25x, keep the second, plus keep the first, differentiate the second. I will actually factor out e to the minus 0.25x, and I'm left with minus 2.5 sine x plus 10 cos x. And for a turning point, we know that this must be 0. So we have to have that 2.5 sine x is 10 cos x. I will divide both sides by 2.5 cos x. I need to show explicitly the division by cos x in order to justify the appearance of the tan x. If you just write the tan x, there is a chance that you will be penalized. So you need to show that it's the division of sine by cosine that's giving you tan here. And you completely ignore the e to the minus 0.25x because that can never give you a result of 0. So that was the first part. And then they show us a sketch of the curve, and then we move on to h of t, which is the absolute value of what we originally had as f of x. And we need to sketch the graph showing the long-term behavior of this curve. So The fact that the modulus there is making everything positive means that we have a function that lives entirely above the x-axis. So it's essentially doing this thing. We have waves that progressively become smaller in amplitude. But you need to notice that the spacing, it remains the same. So it eventually goes down. So we've got decreasing heights. And that was B. And then in C, we need to use this model where we are modeling the height in meters of a ball above ground t seconds after being kicked to find the maximum height of the ball between the first and second bounce. So this is the first bounce here, and this is the second bounce. So we've just been asked to find the height here. Now we know that in the original f of x, turning points were satisfying tan of x is 4. So I will be solving tan t is 4, and I will be looking for the second solution. Why the second solution? Because if I go to the original graph, this is the first solution, that's the second solution, which one reflected, it came up here. So that's the point I'm after. So I will solve tan t is 4, and I'm looking for the second positive solution. So I'm just gonna say t is PV, get the principal value here. So shift tan of 4, and this is giving me a result of 1.3258. Adding pi will take me to the next solution. I want the second solution, we said. So this is giving me a result of 4.47. So the 4.47 is here. Here it was the 1.3258. We need to find this maximum height. So I'm just gonna say that h of 4.47 is simply 10e to the minus 0.25 times 4.47 sine of 4.47. Remember to use full accuracy here. We get an answer of 3.18 meters. In D, we are asked to explain why this model should not be used to predict the time of each bounce. This really takes you back to the idea that the spacing remains constant. This is unlikely to be the case, so that's what we really need to refer to here. We say that times between each bounce are not staying the same. Since heights become smaller. So we've got smaller heights attained after each bounce, and therefore we can't be having the times between bounces remaining the same. Question 13. We are being given here the curve C with this equation. It has two vertical asymptotes at x is 2 and x is minus 3 and passes through the point 3.5. We need to explain why we can deduce that q is 4. Now, we see that the denominator can never be 0. So let's start with that one. So we have an asymptote when 2x minus q is 0 and when we have that x plus 3 is 0. So this is giving me x is q over 2 and x is minus 3. But we've been told that one of the asymptotes is that x is 2. So q over 2 is 2 and therefore q is 4 as required. Now to find the other unknown, if we go back, we were told that we pass to the point 3.5 and we need to find p. So I'm just going to substitute y with a half and x with 3. So I'm just going to say that a half is equal to p minus 3 times 3 over 2 times 3 minus 4 and 3 plus 3. So a half is p minus 9, and in the denominator we have 2 times 3, which is 6 minus 4, which is 2, times 6, which is 12. So 6 is p minus 9, and therefore we obtain that p is 15 as required. Now, in the part B, we need to find the exact value of the area of R. Now, we are integrating from 3, and we need to find the point here. Knowing that P is 15, doesn't take long to reveal that this is 5. So to find R, we need to integrate from 3 to 5. But before we actually do that, we will need to split this down into partial fractions. So we start off by saying that 15 minus 3x over 2x minus 4x plus 3 is going to be a over 2x minus 4 plus b over x plus 3. So 15 minus 3x is a x plus 3 plus b 2x minus 4. I will be substituting x is minus 3. That will give me 24 is minus 10b, and therefore b is minus 24 over 10, which simplifies to minus 12 over 5. And we also use x is 2 to get that 9 is 5a, and therefore a is 9 over 5. So the shaded region R will simply be the integral from 3 to 5 of 9 over 5 over 2x minus 4 minus 12 over 5 over x plus 3. Now this will be giving me ln's, so we've got 9 over 5 ln of 2x minus 4 over 2, I need to divide by the derivative of the bracket, minus 12 over 5 ln of x plus 3, and the derivative of x plus 3 is 1, from 3 to 5. So this is giving me 9 over 10 ln of 6 when I substitute 5 minus 12 over 5 ln of 8, and when I substitute the lower limit it's 9 over 10 ln 2 minus 12 over 5 ln 6. Now we need to end up with ln 3s and ln 2s. So what I could actually do is write this as 9 over 10 ln 2 plus 9 over 10 ln 3, simply splitting 6 as 2 times 3, minus 12 over 5 ln 2 to the power of 3, minus 9 over 10 ln 2, plus 12 over 5 ln 2 plus 12 over 5 ln 3. Now, at least we are almost entirely in terms of ln 2 and ln 3. So this is 9 over 10 ln 2 plus 9 over 10 ln 3 minus 36 over 5 ln 2, the power coming down, minus 9 over 10 ln 2 plus 12 over 5 ln 2 plus 12 over 5 ln 3. And if we do the calculations here, we should be getting 33 over 10 ln 3 minus 24 over 5 ln 2. So we have to match the form of the answer requested in this equation. In question 14, we have that x is 4 sine 2y, so it's x explicitly in terms of y, and we need to find the y dx given that we pass through the origin. So without even checking, we know that 0, 0 is a point on this curve. Now, we can start off by dx dy. So dx dy is simply 8 cos 2y. If I just flip this, I will get dy dx is 1 over 8 cos 2y. And if I evaluate this at x is 0, y is 0, we pass through the origin, remember, it's going to be 1 over 8. So that's the value of dy dx at the origin. Then we need to use the small angle approximation for sine 2y to find an equation linking x and y for points close to the origin. We know it's actually given that sine of theta is approximately theta, provided theta is small and measured in radians. So sine 2y is approximately 2y, and therefore we conclude that x is approximately 4 times 2y, i.e. x is approximately 8y. I'm just gonna write this as y is 1 over 8x close to the origin. So for small values of y. And explain the relationship between the answers to A and BI. Well, the 1 over 8 is the gradient of the tangent, which matches the derivative. So we just need to say that the value in A is the gradient of the line in BI. And then in C, we need to show that dy dx may be written in that form. We have already established that dy dx is 1 over 8 cos 2y. Now, we're not going to write the 1 over cos as sec. I'm trying to bring x back into the game. So we know from the original equation that x is 4 sine 2y. So x over 4 is sine 2y. So I will actually be drawing a triangle here. So if this is 2y and that's a right angle triangle, this is x and this is 4. So this is 4 squared minus x squared using Pythagoras. This means that cos of 2y is simply 16 minus x squared square root over 4. So 8 cos 2y will just be 2 root of 16 minus x squared. I just multiplied both sides by 8. So if I now go back to the given expression for dy dx, all I need to do here is replace 8 cos 2y with the expression we just found, which is 1 over 2 brackets 16 minus x squared. And this matches the form of the question requested, so we can easily say that A is 2 and B is 16. So that was QR paper 1 of June 19. Thank you very much.